Welcome to the Sky Commander Flight Brief. It's your mission-ready podcast for drone pilot training and aerial insights across Canada.
From Transport Canada rules to real-world drone ops, we break it down, take you higher, and help you earn your wings. Because here at skycommander.ca, we don't just fly.
It hints there's more to it. It's a masterclass, a deeper level, maybe a philosophy or a community focus, perhaps.
It's definitely intriguing, sets them apart from just, a basic tips show. Skycommander.ca is the obvious next step. Precisely. If you're thinking about flying a drone in Canada, boom, this content is aimed right at you.
Powered by skycommander.ca.
The elite podcast for Canada's drone pilot. Okay, let's get started. This time we're going all in on what it takes to move beyond just being licensed and become a truly professional UAS operator. We're aiming to cut through some of the noise, focusing on that tricky intersection of advanced field work, the tech itself, and the regulations in both the US and Canada.
That's the goal. Exactly. Total integration. We're trying to synthesize that hard-won field knowledge, things like, why do batteries suddenly die in the cold?
Yeah.
Or how do you actually fly in zero-grid airspace? Yeah. Even the physics behind thermal cameras, synthesizing all that with the legal stuff, the technical mastery the regulators demand. Basically, we want to give you the shortcuts, the insights that separate the pros making real money from, the casual flyers.
Right. And our sources today, they're pretty dense, not going to lie, but definitely rewarding. We've got stuff from advanced operational playbooks, the core FAA Part 107 law itself, detailed guides on airspace authorization, some really crucial US versus Canada regulatory comparisons, and then these deep technical dives into things like high accuracy mapping and advanced thermography. Lots to cover.
A lot.
Okay, let's dive in. Let's start right at the bedrock. Okay, so when we talk about being professional, a huge part of that is having a process, right? Something you can audit, something repeatable. And that process, it has to start with the law. Our sources kept coming back to two foundational rules in Part 107. These govern literally every single flight.
That's exactly right. If you nail these two, you really mitigate a huge chunk of your operational risk right off the bat. First up is 107.15, Condition for Safe Operation. This rule basically says the whole system, aircraft, ground station, links, payload, everything has to be safe before you even think about arming the motors. And, crucially, it has to stay safe during the entire flight. And
the teeth in that rule, Section 107.15, is that it's essentially your emergency brake, legally speaking.
Absolutely. It's the ultimate stop button. If, a motor sounds weird, or you notice lag in the controls, or heaven forbid, your payload shifts midair, right. Boom, you're instantly violating Section 107.05. The law requires you to land immediately, full stop, even if that means putting down in an empty field or a closed parking lot that wasn't your primary landing zone. This rule is your justification, your liability shield for always putting safety first.
Okay, so that's the overarching safety condition. The second rule then connects that legal requirement to the actual stuff you do on the ground before you launch.
Right, that's Section 107.49, pre-flight actions. This one mandates that the pilot in command, that's you, formally checks off a specific list of items before every single takeoff. This isn't like a suggestion. It's a legal checklist. You got to assess weather, airspace restrictions, any hazards to people or property down below. Verify your control links are solid. Check you have enough juice battery power for the whole flight plus reserves. And, this is explicitly called out, you have to ensure you've properly secured all attached objects. Payloads, RID modules, everything.
I really liked how the experts we looked at boiled down the hardware part of Section 107.49 into this handy mnemonic PAR. It makes that pre-flight check really practical in the field.
Yeah, PAR is great. Let's run through it. P is for props. Yeah. Are they secure, undamaged, torqued correctly? The basics, but critical.
Okay.
P, props.
A's antennas.
Are they oriented, right? Are they clear of the frame? Not blocked by carbon fiber, which we'll get into.
Antennas check.
W, sit wiring. Check for strain relief, especially near connectors or anywhere the wires bend sharply. Look for chafing.
Makes sense. Wiring.
E is energy. Batteries. Are they warm, especially in cold weather? Are the cells balanced? And critically, are you planning to land with a decent reserve, like 20, 30%? Don't push it to zero.
Energy. Got it. And the R?
R is RID, remote ID. Is the module working? Is the standard RID aircraft broadcasting? Check it before you fly. In the US especially, that RID status is an absolute go-no-go. If it fails a pre-flight check, the mission's scrubbed right there.
PAR, props, antennas, wiring, energy, RID. Simple, effective. All right, moving beyond just the checklist, a real pro understands why things fail, the physics behind it. Let's start with the airframe and propulsion. Specifically, this idea of crust-to-weight ratio, TW. I know a lot of pilots aim for like 2.1 as a baseline. But what's the actual physics reason that number matters so much?
Right, so TW is simply the total thrust your motors can produce compared to the aircraft's total weight frame, battery, payload, the works. At exactly 1.1, well, you can technically hover, but that's it. No climb, no real control authority. The source material really hammers this home. For confident, predictable handling, especially if there's even a little wind, you need at least 2.1. But, and this is key for professionals, if you're doing heavy lift cinematography or high wind inspections or maybe aggressive mapping flights, you really should be targeting 2.5.1 or even higher.
Why is that extra headroom so important? What does it buy you in the real world?
It buys you control authority, essentially. Your flight controller is constantly making tiny thrust adjustments to hold position or follow commands. If your TW is low, say only 1.5.1, you just don't have much corrective power available. And that leads to a bunch of problems. Clients feel sluggish, the hover isn't stable, and maybe most critically, your braking is mushy. It takes longer to stop or change direction. Plus, think about sudden wind gusts. A strong gust hits, the flight controller screams for maximum power to fight it. If you don't have that headroom, your ESCs, the electronic speed controllers, might get pushed beyond their limits. They could overheat, shut down, or even cause a motor failure mid-flight. So that extra TW is actually a safety buffer for your electronics too.
That choice, the TW you need, often points directly to the kind of motors you should be choosing, doesn't it?
Yeah, absolutely. It's a trade-off. You've got low KV motors. KV is basically RPM per volt. Low KV paired with larger props tends to be more efficient. Better for endurance flights, long mapping missions, carrying heavy payloads. Then you have high KV motors with smaller props. Those are generally better for speed, agility, maybe racing or acrobatic flying. But whichever way you go, you have to look at your ESCs. The rule of thumb we saw consistently is to ensure they have at least 25% current headroom above the absolute worst case scenario draw from your prop and motor combo. So if your math says max draw is 60 amps per motor, you want ESCs rated for 75 amps minimum. Don't skimp there.
Okay, let's switch gears to the invisible stuff, radio links. The source is really focused on the Fresnel zone. This is often misunderstood. How can we explain this fat radio donut idea clearly? People think line of sight is all that matters.
Right, and that's the trap. Line of sight is definitely necessary. You need to see the drone, but it's not enough for a solid link. The Fresnel zone describes how radio waves actually travel. They don't go in a perfectly straight, thin line. The energy spreads out into this sort of ellipsoid or, fat donut shape around the direct path between your transmitter and the drone's receiver. For a really stable link, both your command and control and your video feed, you need to keep at least 60% of the width of that donut clear of obstructions.
So if that donut gets grazed by something, maybe the surface of water, the edge of a hill, a big metal sign,
then you get multipath fade. The signal literally bounces off that object and arrives at the receiving antenna slightly delayed or out of phase compared to the direct signal. The receiver gets confused and your signal quality drops, or you get glitches, dropouts. The really frustrating part is, like you said, this can happen even when you can still clearly see the drone. Your visual line of sight is fine, but the radio path is compromised. The key takeaway here for professionals is you fix link problems with geometry and placement. If your video feed starts flickering when you fly near a metal bridge or a big water tank, the answer isn't to try and illegally boost your transmitter power. The answer is to change your altitude, go up 10, 20 meters maybe, or even just rotate the aircraft slightly. Changing the polarization angle can sometimes clean it right up.
And the irony of modern drone materials.
Right.
The carbon fiber trap.
Oh yeah, it's a classic. Carbon fiber is amazing, right? Super light, incredibly stiff, perfect for airframes, but it's also RF opaque. Radio waves just don't pass through it well at all. It acts like a shield. So if you're building a drone or even just choosing where to mount antennas on a stock one, placing those antennas behind carbon fiber arms or plates is asking for trouble. You create signal dead zones. It often shows up when the aircraft banks or turns sharply. Suddenly an arm blocks the antenna's view of the transmitter and poof, you get a momentary link loss just when you need control the most. The pro solution is always mounting antennas, especially the little stubs, completely clear of the main carbon structure and gimbal cages.
Okay, let's move inside the drone now to the brains and senses, flight controllers and sensors, starting with the compass, the magnetometer. These magnetometer traps seem notorious.
They really are. Your drone's compass, the magnetometer, it's incredibly sensitive to magnetic fields. If you do your compass calibration dance near, say, rebar hidden in concrete, or even just next to your steel tool bag or your car, you're feeding it bad baseline data. It gets corrupted from the start. Then, during flight, if that sensitive compass picks up magnetic noise from other components, high current battery wires running too close, or maybe a powerful video transmitter, VTX, you get a conflict, a compass disagreement. The symptoms, you might see the yaw just sort of snap unexpectedly, or the really classic one is the toilet bowl effect. The drone starts slowly spiraling in GPS hold mode because its understanding of its heading from the compass is fighting with its understanding of its position from the GPS.
So what's the practical advice? How do you minimize that risk?
Separation is key. The general rule, whenever possible, is keep those high current wires and any powerful transmitters at least 5, maybe even 10 centimeters away from the compass module itself. And if you can't physically separate them that much, make absolutely sure all your high current cables are tightly twisted together. Twisted pairs cancel out a lot of the external magnetic field they generate. It makes a difference.
What about those weird phantom altitude changes? The drone seems to climb or descend on its own, even in calm air.
Yeah. That's often barometer drift. The barometer measures air pressure to figure out altitude, right? But it's super sensitive to two things: localized temperature changes and direct airflow. So if the sun is beating down on the flight controller enclosure, baking it, the internal temperature change can mess with the pressure reading, making it think it's climbing or descending. Or, maybe even more common, if prop wash from the propellers is blasting air directly across the little vent hole for the barometer sensor, that creates localized pressure changes too.
I remember reading an anecdote in one source about a crew chasing phantom climbs all day. Turned out the flight controller was mounted right above a big battery that was getting really hot during long mapping flights.
That is a textbook case. The fix, often recommended by manufacturers, especially for higher-end systems, is pretty simple. Try to shade the flight controller if possible. And often, putting a tiny piece of open-cell foam over the barometer vent can work wonders. It dampens the prop wash effect without actually sealing the sensor off from the ambient pressure.
Okay, one last point on hardware, and this loops right back to that pre-flight rule, section 107.49, payload integration and security.
Yes, secure attached objects. It's right there in the law. You absolutely cannot rely on just a single strip of Velcro to hold on a heavy LiDAR scanner or an expensive cinema camera or even just your little remote ID module. Professionals use mechanical backups, safety tethers, locking mounts, redundant straps. Think about it. If that heavy payload shifts even slightly mid-flight, your drone's center of gravity changes instantly. That compromises stability, potentially makes it uncontrollable, and bam, you're violating section 107.20 again because the aircraft is no longer in a condition for safe operation. Redundant fastening for everything. It's non-negotiable.
All right, so we've got the drone itself, sorted, hardware checked, safe, compliant. The next big layer for professional operation is understanding and managing the airspace you're flying in. Let's quickly refresh the basic U.S. airspace hierarchy for everyone.
Sure. Broadly, we split it into controlled and uncontrolled airspace. Controlled is classes A, B, C, D, and E. Flying a drone in most of these generally requires some form of authorization. Uncontrolled is Class G, think GO airspace. That's typically where we operate under Part 107, up to 400 feet above the ground, without needing prior permission, as long as we follow all the other rules, of course.
Let's focus on B, C, and D first. Those are the ones around airports that most often require direct interaction or authorization.
Class B, think big or busy, surrounds the major international airports. It looks like an upside-down wedding cake on charts, extending from the surface up to typically 10,000 feet above sea level, MSL. Authorization is absolutely mandatory. Class C, think city, is around medium-sized airports, often with scheduled airline service, usually surface to 4,000 feet MSL and about a 10-mile radius circle. Again, authorization required. And Class D, think Delta, is for small airports that still have an operating control tower, typically surface up to 2,500 feet MSL, maybe a 4-mile radius. Authorization needed here too when the power is open.
And then there's Class E, the everywhere airspace. This one feels a bit trickier because its floor isn't always the same height.
That's true. Class E is controlled airspace, but it often doesn't have a control tower associated with that specific piece of sky. Out in rural areas, Class E usually starts at 1,200 feet above ground level, AGL. But near airports, especially those with instrument approaches, the floor of Class E can drop down to 700 feet AGL. You'll see that as a shaded magenta border on sectional charts. Or sometimes it goes all the way down to the surface, shown by a dashed magenta line. If you're operating in Class E that starts at the surface, you need authorization just like in B, C, or D.
Okay, and the flip side is uncontrolled airspace, Class G. That's where most routine Part 107 flights happen, right? Generally surface up to 1,200 feet AGL, though we're limited to 400 feet AGL within it.
Exactly. Class G is our usual playground. But even though it's go airspace, professionals know that doesn't mean you skip the safety checks. You still have to do your due diligence scan for local hazards, check for wires or towers, and critically, always check for temporary flight restrictions, TFRs. #, gaining access in controlled airspace.
For pros, needing to fly in controlled airspace is common. Getting that authorization quickly is key. The standard tool for that now is LAAC, right?
Yes, LAAC, the Low Altitude Authorization and Notification capability, has been a game changer. It provides near real-time, often fully automated approval for drone flights within predefined altitude grids in controlled airspace near many airports. You access it through FAA-approved third-party apps. It's generally fast, efficient, and lets you fly up to the maximum altitude shown on the facility map for that specific grid square, usually 400 feet or lower.
But what about the more complex situations? Say you need to fly higher than the LANC grid allows for an inspection, or you need to operate in one of those zero grid areas right next to a major runway where LANC gives you an automatic no. That requires further coordination.
Ah, yes. This is where the real paperwork, the real professionalism comes in. Further coordination is the manual review process. You submit a request directly to the FAA through their drone zone portal. It's the only way to get permission for those zero grid areas or to request altitudes above the published LANC ceiling.
The sources mention this can take time, potentially up to 60 days, so planning ahead is crucial. But what exactly does the FAA need to see in that request to justify, say, flying up to 600 feet and near a Class C airport?
They're looking for a bulletproof safety case. You need to submit a detailed flight risk assessment, often called an FRA. This isn't just saying, I need to fly higher. You need a narrative explaining why the mission absolutely requires that altitude. For instance, we must clear the top of this 550-foot bridge pylon to complete the structural inspection. Then you have to detail your exact procedures, prove your crew is competent for this specific type of operation, and outline your specific mitigation strategies for that increased risk. Things like how you'll contain the drone within a specific boundary, your communication plan, maybe directly with the tower, and documentation showing your aircraft can actually perform safely at that altitude and in those conditions. They are evaluating your diligence and planning, not just the drone itself.
Okay. Beyond the fixed airspace structure, there's the ever-present threat of TFR's temporary flight restrictions. These are the invisible fences that can pop up anywhere, anytime, and they're not on your standard sectional chart. What kind of events trigger TFRs?
TFRs are usually put in place for security or safety reasons that are, well, temporary. Think VIP movements like the president or vice president traveling, national security events. Wildfire suppression efforts often have TSRs to keep drones away from firefighting aircraft, major hazard zones. But the ones that catch out commercial operators most often are the stadium TFRs. These cover major professional and college sporting events. Think MLB, NFL, NCAA division football games, the Super Bowl. Typically, drone flight is banned within a 3 nautical mile radius and up to 3,000 feet AGL, starting 1 hour before the event and ending 1 hour after. And don't forget places like Disney World, which have their own standing flight restrictions that function much like TFRs. You absolutely have to check for these before every single flight.
So let's say you're mid-mission, you did your pre-flight check, everything was clear, but you do a quick recheck on your TFR app, maybe B4UFLY, and boom, a new TFR just popped up over your operating area. Maybe it activated early. What's the absolute non-negotiable professional response?
Land. Immediately. Hard stop. No questions asked. You cease all flight operations instantly. You need to log the exact time you saw the TFR activate and when you landed. Then you notify your client, hopefully referencing a clause you already have in your contract, about TFRs causing potential delays or cancellations. Never, ever try to push the edge or think, I'll just finish this one pass. The FAA tracks TFR intrusions very seriously. As a professional operator, the burden of proof is on you to show you are monitoring TFR status continuously and acted immediately and responsibly to clear the restricted airspace. All right, now we get into what's arguably one of the most complex but increasingly important parts of Part 107 for commercial work. Subpart D, which covers flying over people and moving vehicles. This whole section is built around assessing and mitigating the risk of injury if a drone were to fall.
Before we dive into the specific categories, the sources stress the difference between sustained versus transitional flight. Why is that distinction so critical here?
Because it directly relates to the duration of the risk exposure. Sustained flight over people means hovering, circling, loitering, flying back and forth directly above them for more than just a brief moment. This significantly increases the chance of something going wrong while the drone is overhead. Transitional flight, on the other hand, is just briefly crossing over people while en route from point A to point B, like flying across a road with pedestrians on the sidewalk below, or quickly transiting over a small group to get to the other side of a property. The risk window is much smaller. The rules treat these very differently.
And another tricky definition is the open-air assembly. The FAA hasn't given a hard number, right? So how do pros approach defining that?
Yeah, they deliberately avoided a strict definition like more than 25 people.
So the professional, risk-averse approach is to be conservative. Treat any organized gathering of people outdoors where they can't easily move out of the way. Think concerts, festivals, parades, even crowded farmers markets as an open-air assembly. Operations directly over these are generally prohibited or heavily restricted under most categories. It's important to note, though, there's an exemption for your own crew. Visual observers, the remote pilot, other ground crew directly involved in that specific flight operation are not considered part of the people you're prohibited from flying over.
Okay, so the framework involves assessing risk based on flight type and the group below. The actual authorization system uses 4 categories, right? And for categories 2, 3, and 4, the manufacturer has to provide a declaration of compliance due to the FAA. That's correct. The DUC is the manufacturer, basically certifying that the drone meets the specific safety requirements for that category, usually related to impact energy or design features. Let's start with category 1. This is the simplest, the lowest bar, but it comes with strict limitations.
Right. Cat 1 aircraft have to weigh less than 0.55 pounds, that's 250 grams, and critically, they cannot have any exposed rotating parts that could realistically cut skin on impact. Think prop guards, or maybe ducted fans, or designs where the props stop instantly. If your drone meets both those criteria under 0.55 pounds A&D, no exposed lacerating parts, then you can operate it over people without needing a specific FAA waiver or DUC. Though, importantly, you still need remote ID if you're flying it over an open-air assembly.
Exactly. Now, category 2 starts to bring in physics. It's about kinetic energy.
Category 2 is for drones that, if they were to impact a person, would transfer 11 foot-pounds of kinetic energy or less. Like Category 1, they also cannot have any exposed rotating parts that could cause lacerations. The manufacturer needs that DOC on file with the FAA, and the drone itself has to be permanently labeled as meeting Category 2 standards. The clear intent here is designing aircraft that are unlikely to cause serious injury, particularly head injuries, if they fall.
The practical challenge, honestly, is that as of now, very few drones on the market have actually gone through the process and received this official Category 2 designation from the FAA. So while the rule exists, finding a Cat 2 compliant drone for specific tasks can still be difficult.
Okay, moving up in risk. Category 3. This allows for a higher potential impact energy up to 25 foot-pounds. Because the potential for injury is greater, the operating rules get much stricter.
Which stricter? 2 huge requirements for Category 3 operations that you absolutely have to nail. First, no sustained flight over open-air assemblies. You can only fly transitionally over them. No hovering or circling over that crowd. Second, the operation must take place within a closed or restricted access site. This is crucial, and everyone inside that restricted area must be formally notified that a drone might fly over them.
So let's say you're hired to map a big construction site. It's fenced off. To fly a Cat 3 drone there, you first have to confirm site access is genuinely restricted. Then you need documented proof that every single worker on that site was either briefed in a safety meeting or saw clear, explicit signage warning them about the potential for overhead drone operations. Is that the level of detail needed?
That is precisely the level of rigor required. You need that paper trail. You need proof of notification, verbal warning, written notice, signage, however you do it. You have to document that everyone within that controlled boundary was informed of the risk.
Okay. And finally, the heist level, Category 4.
Category 4 is basically for drones that are treated much more like traditional aircraft in terms of safety assurance. It requires the drone to have an actual airworthiness certificate issued under Part 21 of the FAA regulations. That's the same system used for certifying Cessnas and Boeings. It also mandates a rigorous ongoing maintenance and inspection program. Category 4 is generally going to be reserved for very large, complex, or highly specialized UAS platforms, likely involved in operations like package delivery or other critical infrastructure roles, ## operations over moving vehicles.
Now, how does this category system apply when we're talking about flying over moving vehicles? The definition seemed pretty broad.
It is broad. It covers any vehicle on land or water that is moving and transporting people. So yes, cars, trucks, buses, but also trains, boats, even things like occupied bicycles, or as one source pointed out, vehicles on amusement park rides like roller coasters. To fly over any of these moving vehicles, step 1 is you must be using a categorized drone, Cat 1, 2, 3, or 4. You can't just fly any old drone over traffic. Then you have 2 operational paths, similar to Cat 3 over people. Option A, you are operating within a closed or restricted access area, and everyone in the vehicles within that area has been put on notice. Think maybe a closed movie set or a secured industrial facility where vehicle access is controlled. Option B, if you're not in a restricted area, say flying near a public road, then you can only fly transitionally across the path of the moving vehicles.
Meaning you can quickly fly your drone across a highway to inspect something on the other side, but you absolutely cannot hover over a car driving down that highway or follow it.
Exactly. No sustained flight over moving vehicles in open areas. Only brief transitional crossings are allowed under the standard rules.
All right, this is crucial for anyone working near the border or considering international jobs. We need to understand the differences between the U.S. system FAA Part 107 and the Canadian system managed by Transport Canada, which uses the RPAS rules under CARS Part 9. And things are changing fast, especially regarding advanced operations like BVLOS. Let's start there. What's the current state of play?
Both countries are definitely pushing towards making advanced operations, particularly beyond visual line of sight, BVLOS, more routine and standardized. In the U.S., the big news was the FAA releasing the BVLOS Notice of Proposed Rulemaking, the NPRM, back in August 2025. This proposal aims to create a more streamlined, risk-based path for certain types of lower-risk BVLOS flights, moving away from the current system that requires complex one-off waivers or exemptions. But it's still just a proposal. Until that rule is finalized and implemented, BVLOS in the U.S. remains largely in the realm of waivers.
Canada seems a bit further ahead with a concrete timeline, right?
Yes. Transport Canada has laid out a clearer path. They're rolling out brand new operational profiles set to take effect on November 4, 2025. This introduces standardized terminology and procedures for things like EV loss, extended visual line of sight, sheltered operations, flying within controlled environments like under bridges or inside buildings, and a new category called Level 1 Complex, which is designed for lower-risk BVLOS scenarios. To conduct these new types of operations, Canadian pilots will need to obtain an RPAS Operator Certificate, RPOC, which involves demonstrating robust safety management systems. This is a big shift, standardizing operations that previously required very complex, bespoke, special flight operation certificates, or SFOCs, #tag key operational differences, the gotchas. Okay, so the advanced stuff is evolving, but let's get into the practical day-to-day differences, the gotchas that can trip up an operator working in both countries. Altitude seems like a big one. Huge difference. In the U.S., under Part 107, we're used to the 400 feet AGL limit, but we also have that provision allowing us to fly 400 feet above a structure as long as we stay within 400 feet laterally of it. So inspecting a 400-foot tower, you could potentially fly up to 800 feet AGL right next to it. That plus 400 feet over structures rule does not exist by default in Canada. Their standard limit under the RPAS rules is a strict 400 feet, which is 122 meters AGL, period. If you fly to 500 feet AGL next to a tall building in, say, Vancouver, without specific authorization, you are violating their rules, even though it might feel normal to a U.S. pilot. You need explicit permission from ND Canada to exceed 400 feet AGL there, regardless of nearby obstacles.
Another major divergence right now is electronic identification.
Yes. Remote ID, RID, is now mandatory and actively enforced in the United States for virtually all commercial operations outside of designated FRIA zones or specific waivers. Your drone must be broadcasting its ID and location info. If it's not, you're grounded. Canada, however, does not currently mandate remote ID. Transport Canada is looking into it, exploring options, but as of today, it's not a requirement for flying drones in Canada. So a U.S. operator needs RID capability for U.S. jobs, but doesn't necessarily need it for Canadian jobs, though they still need to follow all other Canadian rules.
Which brings us to getting airspace authorization itself, different systems.
Different systems, same goal. The U.S. uses LANC for near real-time automated authorizations in many areas, backed up by the manual drone zone portal for more complex requests. Canada uses Canada's MV drone platform. It's their dedicated app and web portal for pilots to request access to controlled airspace. You need to know how to use the correct system for the country you're operating in.
We talked about the complexities of flying over moving vehicles in the U.S. restricted, but sometimes possible with waivers or under specific conditions. How does Canada handle operating from a moving vehicle?
Much, much stricter. In Canada, it is explicitly prohibited to operate your drone, RPAS, while you yourself are simultaneously operating a moving car, boat, or even a manned aircraft. Full stop. This basically kills those cool cinematic follow shots taken from a moving car or boat unless that vehicle is completely stopped or anchored. That's a really significant operational difference, especially for filmmakers or inspectors planning cross-border projects.
Okay, and finally, let's compare the fundamental approach to flying near people. We have the U.S. kinetic energy categories 1 through 4. What's Canada's model?
Canada uses a different philosophy. It's based primarily on pilot certification level and defined standoff distances, rather than calculated impact energy. They have two main pilot certificates, basic and advanced. To get closer to people, you generally need the advanced certificate. But even then, the privileges are often tied to the manufacturer having filed a safety assurance declaration for that specific drone model, proving it meets certain safety standards. And critically, Canadian rules often rely on explicit standoff minima.
Can you give an example of that standoff difference?
Sure. For many standard advanced operations in Canada, the ones allowing flight closer to people than basic operations permit the rule, often requires the drone to maintain a minimum horizontal distance of 30 meters, it's about 100 feet, from any person not directly involved in the flight operation. It's a defined spatial safety bubble. Whereas the U.S. system, like we discussed, focuses more on the potential injury based on the drone's weight and impact characteristics, categories 1 to 4. So a U.S. pilot flying a tiny sub-250-gram drone might feel comfortable flying quite close to people under U.S. Cat 1 rules, but if they fly that same drone in Canada, they'd likely still need to respect that 30-meter buffer for advanced operations, unless operating under very specific exemptions. Looking at both systems, despite the differences, they reinforce what we might call the 3C plus 2P litmus test for professional discipline. You always have to demonstrate control, proven fail-safe, predictable handling, containment, defined operating areas, safety buffers, compliance, having the right authorizations, following the rules, proof, meticulous logs, document procedures, and prioritizing people. Safety above all else. Honestly, one of the best takeaways for a U.S. operator looking at the Canadian system is adopting their formal site survey rigor. CRR 901.27 in Canada mandates a very thorough documented site survey before flight, identifying boundaries, obstacles, potential hazards, airspace, weather checks, emergency procedures, everything. If U.S. pilots adopted that level of formal, documented site survey for every job, it would massively strengthen their Section 107.49 pre-flight records and overall professionalism.
Okay, we've covered the legal frameworks, the hardware basics. Now let's get into some specialized types of flying that really demand deeper technical knowledge. Starting with thermal imaging mastery. It seems like anyone can buy a thermal camera now, but using it effectively is another story.
That's absolutely true. The fundamental thing to grasp is that thermal cameras don't see visible light. They see invisible infrared energy, which is essentially heat. And while heat is energy, it doesn't behave the same way light does. For instance, visible light obviously passes straight through a clean window. But thermal energy, specifically the long-wave infrared, LWIR, that most drone thermal cameras detect, generally does not pass through standard architectural glass. It also doesn't see through solid walls.
So if I'm looking at a thermal image of a building's exterior, what am I actually seeing if not the heat inside?
You're mostly seeing a surface phenomenon. You're seeing the temperature of the exterior surface itself. That surface temperature might be influenced by heat transferring from inside, like where insulation is missing, or over wall studs, or might be influenced by solar loading, or very importantly, by reflections. This is where understanding emissivity becomes absolutely critical.
Right, emissivity. Explain that and why it causes so many bad readings or misinterpretations in thermography.
Emissivity is basically a measure of how efficiently a material radiates thermal energy. It's a scale from 0 to 1. High emissivity materials, things like wood, concrete, asphalt, painted surfaces, even human skin are very efficient emitters. They radiate heat well, so the camera gets a reasonably accurate reading of their surface temperature. These are usually around 0.95 emissivity. Low emissivity materials, however, things like shiny unpainted metals, aluminum foil, polished stainless steel, are poor emitters. They don't radiate their own heat very well, but they are highly reflective in the infrared spectrum. So when you point your thermal camera at a shiny metal surface, you're often seeing mostly a thermal reflection of the surroundings, not the actual temperature of the metal itself.
And this directly leads to that common pitfall the sources mentioned. Glass is a liar in thermal imaging.
Totally. Standard window glass has low emissivity and is highly reflective in the long-wave infrared spectrum. So if you see a bright, seemingly hot spot on a window of a building, especially during the day, don't immediately assume it's heat leaking out from inside. It could very well be a reflection of the sun, a warm patch of pavement nearby, or even the warm sky itself. Conversely, at night, clear sky is often extremely cold in the thermal spectrum. Its reflection off a window can make the window appear intensely cold, dark blue or purple in many palettes, which pilots might mistakenly interpret as massive heat loss or a broken seal when it's just a reflection of the cold night sky.
Which means for professional thermography work, just taking a picture isn't enough. The data logging requirements are much more stringent.
They absolutely have to be. A professional thermal report can't just show a temperature reading. Your logs, and ideally annotations on the images themselves, need to include critical metadata. The emissivity value you assumed for the surface you measured, the reflected apparent temperature, you measure this by pointing the camera at a known reflector like crumpled aluminum foil, the ambient air temperature, wind speed, wind-cool surfaces, and the sun conditions, solar loading. Without logging and considering these factors, those hot spots or cold spots you find are basically meaningless. They can easily be artifacts of reflection or environmental conditions, rendering your expensive thermal inspection invalid or misleading. #check, #high accuracy mapping workflows, RTK versus PPK.
Okay, let's pivot from thermal to another high precision task, high accuracy mapping. We're talking about creating maps and models with sub-inch accuracy, often needed for surveying or construction progress tracking. This requires precise GPS or more accurately GNSS corrections.
Just exactly. Achieving survey-grade accuracy from a drone isn't automatic. It requires mastering the entire workflow, starting with flight planning. To get that sub-inch ground saddle distance, GSD, which relates to image resolution, you typically need to keep your flight altitude relatively low, often at or below 200 feet AGL. Also, for creating detailed 3D models, especially of vertical structures like building facades or cliff faces, pros often use oblique camera angles. Instead of just pointing the camera straight down, nadir, they'll fly orbits around the subject with the camera tilted, maybe 15 to 30 degrees off nadir. This helps capture the sides of features and avoids weird reflections you can get from shooting smooth surfaces straight on.
And to get the positional accuracy, we rely on correcting the drone's GPS data. The two main methods are RTK and PPK. What's a practical difference, and when would you choose one over the other?
RTK stands for real-time kinematic. This is often the preferred method when possible. It requires a constant, reliable data link, usually internet via a cellular hotspot, between the drone and a ground-based GNSS base station, or a network correction service. The base station calculates corrections based on its known fixed position and sends them to the drone in real time during the flight. The drone uses these corrections instantly to record highly accurate geographic coordinates, geotags, for each photo it takes. The big advantage is you get accurately tagged photos right off the drone. The disadvantage, if you lose that internet connection or radio link to the base, you lose the RTK correction.
And the alternative for when you don't have that solid real-time link is PPK.
Right. PPK means post-process kinematic. This is your go-to method when you're flying in areas with poor or no cellular coverage, or if you just want a more robust backup. With PPK, the drone still needs to communicate with a base station, but it doesn't need that link to be live during the flight. Instead, both the drone and the base station simply log raw GNSS satellite observations during the mission. After landing, you download these log files, often called OBS and MRK files, from both the drone and the base station, and you use specialized software on a computer to combine them and calculate the precise coordinates for each photo after the fact. The key thing to remember with PPK is convergence time. The GNSS receiver needs time to lock onto enough satellites and gather enough data to calculate a highly accurate position. So PPK flights often need to be a bit longer, maybe 10 minutes minimum, ideally more, to ensure you get good quality data for post-processing. A really short 2-minute PPK flight might not yield great results.
Okay, one last crucial piece for mapping accuracy. The difference between GCPs, ground control points, and checkpoints. They sound similar but serve very different roles.
Very different, and both essential for professional results. Both GCPs and checkpoints are points on the ground whose precise coordinates you've measured using survey-grade GNSS equipment, like an EMLID RS-2 rover talking to a base station. They need to be clearly visible in the drone photos and have a fixed, reliable position not too close to buildings or trees that could block satellite signals. Now, GCPs are used during the photogrammetry processing. You tell the software, this pixel in these photos corresponds to this exact known coordinate on the ground. The software uses these GCPs to anchor, scale, and orient the entire map or 3D model accurately to the real world. You typically need several GCPs spread across your project area. Checkpoints, on the other hand, are points you've also surveyed accurately, but you deliberately do not tell the processing software about them. You hold them back. After the map or model is fully processed using the GCPs, you then use the known coordinates of the checkpoints to independently verify the accuracy of your final product. You measure the coordinates of the checkpoint location in your generated map and compare them to the surveyed coordinates. This tells you your actual error. Maybe the horizontal XY error is half an inch, and the vertical Z error is 1 inch. If your checkpoint errors meet the project requirements, you know your map is good. If they don't, something went wrong in your workflow, and the map isn't valid. Checkpoints are your quality control. #tag mastering abnormals, fixing problems in the field.
Okay, we've covered a lot of planning and tech, but the real mark of a pro isn't just perfect flights. It's how you handle things when they inevitably go wrong. Let's quickly run through some common abnormal situations and the practical fixes from the field.
Good idea. First up, you're flying near a building with lots of glass or metal, and suddenly your video feed gets choppy or drops out. Multipath.
We talked about the Fresnel zone earlier.
Exactly. That's almost certainly the cause. Your immediate fix is change the geometry. Climb 10 or 20 meters, get higher to lift that Fresnel zone donut above the reflective surface. Or sometimes just rotating the aircraft 45 or 90 degrees can change the antenna polarization relative to the reflection and clear it up. Don't just keep flying blind.
What about that scary compass fight the drone starts doing that yaw twitch or the toilet bowl spiral we mentioned?
First thing, switch to a less GPS-dependent flight mode immediately. Go to ATI mode or even full manual if you're comfortable and the aircraft supports it. Regain positive control first, then climb. Get away from potential ground-level magnetic interference. If the problem continues even at altitude, it's likely internal noise. You have to land safely as soon as possible. Then, back on the ground, investigate potential noise sources near the compass, usually the VTX or power wires, and try to reroute or shield them. That 5-10 centimeter separation rule is key.
For the LiDAR folks, you're mapping, and you notice on the downwind leg, where your ground speed is highest, the resulting point cloud looks smeared or sparse point smear on tailwind legs.
Yeah, that's because the ground is moving past the sensor too quickly for the scanner's current settings. The points get stretched out. The fix is straightforward. Either reduce your planned ground speed for the mission, especially on those fast legs, or, if your LiDAR sensor software allows, increase the scan rate points per second to compensate for the higher speed and maintain your desired point density.
The big one, lost link. Control or video signal just drops completely.
This is why pre-mission briefing is absolutely critical. Everyone on the crew, especially the pilot, must know exactly what the drone's pre-programmed VIL-safe action is. Is it set to RTH? Return to home. Hover in place. Or land immediately. If RTH is the plan, the most crucial part of the pre-flight check was confirming that the preset RTH altitude is high enough to clear all potential obstacles along the likely return path. That includes the highest point of the structure you're inspecting, nearby trees, power lines, rooftop HVAC units, antennas, everything. Never assume the default RTH altitude is safe for your specific site. Verify it.
And finally, an environmental one. Hot summer overheat. You get a temperature warning for the IMU or flight controller on a hot day.
Land immediately. Don't push it. Get the drone into the shade to cool down. Proactively, on really hot days, you should plan for shorter flight legs. Maybe land when the battery hits 30% or even 35% reserve instead of pushing it down to 20%. Why? Because drawing power from the battery heats it up, especially in the last third of its capacity. A hot battery sitting inside a hot drone enclosure adds to the thermal load on sensitive electronics like the IMU. Landing earlier keeps internal temps lower. And monitor your battery health. High internal resistance, IR, means a pack is working harder and generating more heat. Retire aging packs. Pulling all this together, this entire deep dive, being a truly professional UAS operator, it really boils down to integrating this kind of deep technical understanding, knowing why the Fresnel zone matters, understanding emissivity, calculating TW ratios with absolutely rigorous adherence to the regulations. You have to treat rules like Section 107.15 safe condition and Section 107.49 pre-flight actions, not just as rules, but as legal frameworks that justify every piece of gear you choose and every single action you take in the field. Every decision, from calculating your thrust margin to meticulously documenting your Category 3 notifications, it all builds that essential bulletproof paper trail.
And here's where it gets really interesting, especially thinking about the future, those BVLOS and EVLOS operations becoming more accessible. The key to actually getting approval for those advanced privileges, it's not just going to be about having the most expensive drone with RTK or the manufacturer's fancy safety paperwork. The sources suggest, and it makes sense, that the real key will be the demonstrated rigor of your documented procedures. When the FAA or Transport Canada looks at a waiver application or an RPOC submission, the difference between getting a yes or a no is often going to come down to the quality, the consistency, and the sheer detail of your documented risk assessments, your pre-flight logs, your maintenance records, your crew training.
That documented rigor really is the only pathway to scaling safety reliably. especially when you can't physically see the aircraft anymore.
That's a wrap on today's mission, Commander. See above, go beyond, get ahead. For more training, tools, and intel, head to skycommander.ca. If you learned something new, share it, subscribe, and leave us a 5-star debrief.